I'll just kind of run through this quickly. This is what we've been talking about for a few weeks now. We have velocity, momentum, and like changes in momentum as a result of forces. This is all linear, and these are all vector equations, right? So each one of these, we have an x and a y component. So even though these are relatively simple, they're just like 3 variables in each, we know that we can get quite a lot of material out of these like momentum charts, and there's a lot of power in these tools here and a lot of subtleties to the way we apply these things. But at the end of the day, they're just, three equations. A change in position over time, multiply that by mass, and then see how that changes as a result of forces over time. However, this isn't the whole story for motion, or just like the physics of how things move. Why? Well, if we take a look at, first ignore rotation here. Just imagine we have like a ball, an object sliding down maybe like a sheet of ice or something like that. We know how to describe that so far, right? We have an angle of the plane, we can find its speed, we can break that into 2 components of velocity if we want, we can find the kinetic energy of this, we can find the force due to gravity and how much that's going to affect its velocity, all these great things linearly. But that isn't the whole story, because what if we allowed the thing to roll? Now all those other things we can have that we had, like sliding, like its translational velocity, its change in velocity, the components of it, all those things can be the exact same. Let's say like the center of mass of this thing is still moving at the same exact speed down the ramp, except now it's also spinning. So all of the equations we just talked about, or all the quantities we just talked about that we know how to calculate, would still be true. However, now we have this additional rotation. And I guess we haven't really proved it, but that we want something to describe the difference between those 2 scenarios, right? That rotation is like physically meaningful. It's mass that's moving around. It turns out to have some momentum and some energy associated with it that are completely independent of our linear quantities. And that kind of works out just the way like x and y are independent for the linear quantities. We can solve x, we can solve y. We can do a similar kind of thing when things are translating and rotating, where we can kind of separate them and with one hat on, talk about how fast it's rotating, how that's changing and stuff like that, and with the other, talk about how the overall thing is translating. So today, we're going to build up the way to talk about the rotational side of things, and it turns out to very closely like kind of be analogous to the linear side of things. We just need kind of a new language to talk about these things. So we'll go through these all in much more detail, but very roughly, instead of velocity, translations over time, we have angular velocity. So this curly W, omega, is angular velocity, and instead of translations, change in position, which is our delta x, we have delta theta, or a change in an angle. It's just how much something rotates over an amount of time. What do we do in linear, like going from velocity? What else is important, right? When we're describing motion, we decided that the mass was important, right? 2 things moving at the same speed or same velocity, the one with higher mass has more momentum, and that's very physically important. Same thing goes with rotations, so we have angular momentum. So L here is angular momentum, and we get it by multiplying our angular velocity, omega, by I, which is like our rotational mass. We call it our rotational inertia. It's also called moment of inertia. I'll use both of those terms interchangeably, rotational inertia and moment of inertia. But you multiply your angular velocity by your rotational inertia, and that gives us our angular momentum. So we have 2, like let's say a carousel rotating and this chair rotating with the same angular velocity, right? So they complete one full rotation in the same amount of time. We haven't done any math yet or decided how to calculate this rotational mass or anything like that. But I think we all have some intuition that the carousel should probably carry more angular momentum than this chair, right? And that turns out to be true. And we'll just have to uncover what physical characteristics make that true. Yeah?
So L is the angular momentum.
Right.
Rotational inertia.
L is the angular momentum. I here is the rotational inertia. So it's like that's rotational inertia is the rotational mass. Okay. So moment of inertia is another phrase for it.
Okay, thank you.
And it's also important to note I is a scalar, just like mass. It's just a number. There's no direction, right? You have 5 kilograms. That's it, not 5 kilograms north or something. Same thing with moment of inertia. We just have a value of moment of inertia. And so that tells us that the angular velocity and the angular momentum are in the same direction, which makes sense. Same thing with linear. If something's moving, its velocity is in the positive x direction. Its momentum is also in the positive x direction. And that's going to be true about angular momentum as well. And then finally, we have a way to describe what an instantaneous angular momentum is, but that can change when we do something to an object, right? We can change how fast it's spinning or the direction, and we do so not by applying a force, but applying a torque. So a torque, this tau, was like a curly T thing, but if you apply a net torque on something, which is our angular version of a force, over a time, then you change its angular momentum. So L is angular momentum. Delta L is just the change in angular momentum. So if I apply a torque over time, I get a change. And just like the change in momentum is in the same direction as a force, right? So if I apply a force in positive y, the change in momentum will be in the positive y direction. Same thing, if I apply a torque in one direction, delta L is going to be in the same direction as that net torque. And we can just add delta L to whatever L we started with and find the new resulting angular momentum after we apply a torque. So a lot of things we left out here, like we kind of just generally talked about the analogy here, but one glaring hole in that is, what do these vectors mean? Like, how do we talk about rotations as a vector? How do we describe the direction? So that's one thing we'll have to discuss. We also have no idea what I is, or like rotation. We know it's rotational inertia or moment of inertia. We don't know how to calculate it. So there's a lot of work to be done, but just so you can see where we're going is to develop the same framework. Theta is just the angle. So just like x is 3 meters, theta might be 30 degrees or something like that, which actually perfectly moves us into just how do we describe angles. So far we've been using degrees, and so degrees, but now we're going to use radians. The reason we'll demonstrate soon, but radians are actually like unitless. So when you have radians in a problem, you can just multiply them by by physical units, and it doesn't change them. We'll see what that means soon. But you should know, like, one full rotation is 360 degrees, right? That's going around a clock or spinning in a circle, whatever. 360 degrees is equal to 2 pi radians. So one full rotation is 2 pi, meaning pi over 2 is the same as 90 degrees or a quarter rotation. Pi is 180 degrees or half a rotation. So it's good to get comfortable going back and forth between these, even though in this unit, when we're talking about angular velocity and momentum and stuff like that, we will be using radians. So another thing to take away from that is, for something on the final where you'll have problems that use both degrees and radians, it's a good idea to know how to make your calculator switch back and forth between those two. We got a lot of questions on quizzes like, do you know how to switch back and forth? And the answer is no. I use my computer for everything now. I don't know how to work a calculator. So please figure out how to do that. Okay, so describing the angle, now that we know how to do it quantitatively, or like numerically, I guess, with radians, just describing the angle. But how do we describe the direction, right? So how do I differentiate this angle from this angle, or if you're listening to it like clockwise from counterclockwise, stuff like that. So yeah, what about using clockwise and counterclockwise? That is the way we normally communicate. If I wanted to tell you which way to spin, I would say clockwise or counterclockwise. But that turns out not to be a great idea because we need something that's the same for all observers. And what I mean by that is, like, if we're just talking about linear motion and I say something is moving in the positive x direction, which I'm going to say is this way, toward this side of the room, we're all going to say that's the positive x direction. Whether it's you facing me this way or me facing you, it doesn't matter where we're sitting. We can all agree that that is positive x. Whether I'm in the basement, on the roof, this is positive x, no problem. However, let's try talking about rotations in terms of clockwise and counterclockwise. So I'm spinning this wheel, and let's pay attention to which way the blue tape is moving on this wheel. And so from this perspective, all of us would say this is what? Clockwise or counterclockwise? clockwise, right? But now, wheel's still spinning in the same direction on this axis. I'm going to turn this table around, simulate us all going behind the desk. Now which way is this thing rotating? Counterclockwise, right? And if I came on this side here, I say clockwise, you're all saying counterclockwise right now. So it's not a great way to describe rotations when we are doing physics, because again, if you're working on a physics problem at the front of the room and I'm working on a physics problem at the back of the room, we want the same answer. And so this doesn't work. What about just like if I pick a location on the object and describe the rotation by the direction that that's moving? So like I said, we all agree that like this side of the room is plus x. So what if I just say, okay, this piece of tape, when I rotate this, is moving in the plus x direction. So why don't I just say this rotation, this clockwise rotation from this perspective, why don't we call it plus x? Because we all agree on that. If you're here and it's moving, you say it's plus x, I say it's plus x. But now let's wait a sec, let the wheel rotate. Now this same piece of tape is moving down. And now it's moving to the left. And now it's moving up. And now it's moving right. So what I'm trying to say is we can't describe the rotation based on what any individual piece of the object is doing, because that is going to change in an instant, and it's constantly changing. And so that doesn't work either. What does stay the same? So what, like when I rotate this wheel, everything on this wheel is moving, constantly changing directions. What part of the wheel is staying the same? What about this is constant? Anyone want to take a guess? So this piece of tape, we said we can't describe the direction of rotation based on what the tape's doing because it's always changing. What part of this wheel is not changing? Yeah, the center. And so that's kind of a step in the right direction for us, is that the axis of rotation is this constant, right? What the thing at the absolute center, the axis, isn't changing. We're rotating around the center axle of the wheel, and so that's a good place to start. We want to describe something about the axis of the wheel, and it turns out that that's exactly it, that the axle defines an axis. So the axis of rotation, and what I mean by that is just like a line extending straight through. And just like x or y, that gives us an axis along which I can have positive values and negative values. And the way we assign those positive and negative values is the right-hand rule. So we're defining rotations about some axis, right, as along that axis. And so in this case, if you imagine this wheel is like on a page, they can be into the page or out of the page. We describe that with these two symbols here, the X in a circle or the dot in a circle. The way I was taught to remember that is like if you imagine an arrow coming toward you, like out of the page, you'd see the tip, so a dot. And if you see an arrow like going away from you, like into the page, you'd see the feathers, you'd see the cross. But either way, these are the two symbols. And it's really just another axis. We have X horizontal, Y vertical, and then into and out of the page. Or like the Z axis is something that we normally call it in other math classes. But so it's like we're kind of working in like pseudo 3 dimensions. We're not going to do anything where like, we're not going to do like true 3-dimensional algebra, calculus, anything like, well, we do no calculus. But so now we'll just add this new quantity of like into and out of the page. And that's just so we can have an axis that's set aside for the direction of rotation. However, we don't always have to have something that's rotating in the plane of the page, in which case the direction would be into or out of the page. We can also have something like what's drawn on the board here, where it's rotating kind of like flat, in which case the axis of rotation is what we would normally call the y-axis. Right? So rotations can be in the y direction or the x direction as well, but now, we still have this into and out of the page direction where now the object is sitting. So I should probably introduce at this point the right-hand rule. I know you've seen this in DL, right? You've worked with the right-hand rule a little bit. So like I said, that's just to decide which way is like positive and which way is negative, if you want to think of it that way. And so we just take our right hand, wrap our fingers around the axis of rotation, in the direction that the object is rotating. So looking at this disk that's on the board, if we wrap our fingers around this center axis in the direction that it's rotating, which from our perspective is counterclockwise, we should all get up. That the direction of this rotation, so that change in angle, the angular velocity, the angular momentum, whatever, all of these things are oriented upward because of the direction of rotation. Or if we take a look at this wheel here, if I spin it this way, if we wrap our fingers around the axis of rotation in the direction of the rotation, we should get that the angular velocity or angular momentum of this wheel is pointing to the front of the room. And if I flip the direction of the rotation, I'll get that it's pointing toward the back, right? So that is kind of showing us the value of this method here, that this right-hand rule, one, we all agree, and let's test that. Now I'm behind it and you're in front of it, so before we got opposite answers. But for me, this is toward the back of the room, and I encourage you all to try this. In fact, whenever you can check yourself on the right-hand rule, you should. It takes a bit of practice, and we'll keep making mistakes for a while. But you should all also get that this is going toward the back of the room. If we wrap our fingers with the rotation around the axis, and so we agree on it, and so this does like kind of two basic things. One, everyone agrees on it. Two, if I flip the direction of rotation, I flip the direction of the angular velocity vector, right? This direction is front of the room. This direction is back of the room. So that makes sense, right? They're along the same axis, and we just get kind of negative or positive. It doesn't really matter which one is negative and which is positive, so that's why I'm saying it's like a kind of pseudo-third dimension. All that we care about is that they are opposite each other. So when we're working with like angular momentum or torques or stuff like that, we're really just going to worry about, is this like increasing or decreasing? If you add into the page to out of the page, they'll cancel each other out. If you add out of the page to out of the page, they'll add to each other. Same with into the page, into the page. It doesn't matter which one is positive or negative. Again, they're just that they are opposites. Another thing about the right-hand rule, if you find yourself like kind of contorting your hand a lot, there's probably an easier way to do it. So if you find that you're causing pain, stop, reset, and there's probably an easier way to orient your hand. All of us will, one time or another, accidentally use our left hand, and you'll just get the wrong answer, just like the opposite. The left hand produces the exact opposite answer as the right hand. The reason we use the right hand is just convention. So we use a right-handed coordinate system. There's nothing inherently, there's nothing physically correct about using our right hand to describe the axis of rotation. It's just we all need to agree on one hand to use, otherwise we'll not agree on our answers. Okay, so let's do a little practice on this. We have a car moving here to the right. What direction do the angular velocity vectors of the wheels point? So we have wheels rotating as the car moves to the right. What direction are their angular velocity vectors? When you decide, see if your neighbor agrees. So if you need a little help visualizing, if this car is moving to the right, its wheels should all be rotating like this, right? And what direction is this angular velocity? Well, we wrap our hand around the center of our right hand, around the axis of rotation, fingers in the direction of the rotation, and we should get into the page. Right, so so I asked about the angular velocity, but this would also be true about delta theta, right? So the change in angle over time of these tires, theta is growing in this direction, so that's into the page. Theta and angular velocity are in the same direction because they're just related by delta t. And then similarly, angular velocity is just related to angular momentum. by multiplying by another scalar, the moment of inertia, which we haven't talked about yet, but we know it's just a number. And so angular momentum is in that same direction into the page. Yeah.
So the reason it's into the page is because when we were doing it, like this, our thumb goes into the page.
Exactly, yeah. The thumb points in the direction of the vector that you're trying to describe. So I guess that maybe I didn't say that clearly. The direction that we're assigning here means the direction of the vector. So these are all vector quantities, right? If I have a velocity, I just draw the arrow in the direction of the motion, and its length is determined by how fast it's moving. Same thing here. If I wanted to describe angular velocity, my vector that I'm going to draw is in the direction of the angular velocity. So here it's into the page. So you could draw like a bigger or smaller circle with a cross in it, something sometimes people do, or just write the number next to the cross with the arrow in it. But what we're really saying is that vector points into the page, and the faster that it's spinning, the longer the arrow will be, the larger the angular velocity. So we've just determined this new axis for the angular velocity to point. Okay. Questions on this example here? So we'll do a lot more practice with this. So now diving more deeply into each one of those angular velocity, angular momentum, and changes in angular momentum. First, our angular velocity. So again, it's this quantity omega. So this is like v velocity. It's just like a curly w, lowercase omega, and it's equal to the change in angle over time. So here, like we just have a wheel that's rotating. In this case, the direction, we should all use our right hands and see that the direction here is out of the page. And so if our delta theta, like here, is opening up like this, we get out of the page, and our angular velocity is similarly out of the page. Here we can see why radians are valuable, or I guess start to see. If I plugged in a theta or a delta theta that was in degrees, so like maybe 60 degrees in 4 seconds or something like that, I would be left with units of degrees per second. So I guess maybe we don't see why that's an issue quite yet, but we don't want degrees floating around. If we think about our quantities that are important to us in the metric system, like joules, like force, joules, power, stuff like that, energy, degrees don't show up anywhere, right? So we want to get rid of them, and so that's why we use radians. And radians, like they're kind of this like shadow unit. We'll often write radians per second or something just to emphasize that we're talking about rotations or like angle per second. But truly, the units of omega are just inverse seconds. So radians are, like I said, kind of a phantom unit. If I divide 2 pi by seconds, I just get 1 over seconds. So let's do a little practice with that. What is the angular velocity of, so I guess I should say the hour hand on this clock. So we have just a normal analog clock here with an hour hand moving around. Takes 12 hours to go once around. What is the angular velocity in inverse seconds or radians per second? And if you don't have a calculator, just write out the expression and decide, should it be really big? Should it be medium? Should it be really small? Be 30 more seconds with this one. Okay. So Does an hour hand on a clock rotate very quickly? No. So I mean, I guess that's quickly is very relative, but we know that our units are like radians per second, right? So radians are measured by pi, like 2 pi is a full rotation, so 2 pi is what, like 7 or 6-ish, something like that. But 6-ish divided by however many seconds it takes for an hour hand to go around, it's very small. So I don't know, very qualitatively and roughly, the angular velocity of this hour hand should be very, very small because it takes a lot of seconds for it to go around. And if we were to do that explicitly, angular velocity, omega, is our change in angle over a change in time. And so first of all, if we just getting the direction part out of the way, this is a vector. And so we have an hour hand. And so from this perspective, it's moving, well, by definition, clockwise. And so if we wrap our fingers with the direction that that hour hand is moving, we get into the page. So that's why all of these vectors are oriented into the page. And now I can evaluate this. My delta theta, let's just pick one full rotation, which is 2 pi. And so if my full rotation is 2 pi, the amount of time it takes the hour hand to do that is 12 hours. And so I asked for it in inverse seconds, or radians per second, so I need to do 12 hours and convert that to seconds. So times 60 minutes an hour, times 60 seconds per minute, and I get this tiny number for my angular velocity into the page. So yeah, this is just an exercise in plugging things in here and seeing that our units are inverse seconds. Questions here? Okay, now let's take a step further and go on to angular momentum. So we know how to calculate angular velocity, how quickly something's rotating. Now we want to distinguish between, like we said, like a carousel and a chair rotating. They have very different masses, and we have this idea that they need different angular masses too, some other equivalent. And that's, like we said, our rotational inertia, or moment of inertia, this value I. So we multiply our angular velocity omega by I, and we get angular momentum. So I tells us like how hard it is to rotate something, or how hard it is to stop something from rotating. And yeah, so L describes the angular momentum. So let's figure out how to calculate rotational inertia I. So this is the expression for it. It's the sum over mr squared. And so this sigma sum just means we're summing up all of the pieces of an object, so each mass element. So I take each mass element, and for each element I add up its m times r squared, where m is the mass of that mass element, and r is the distance from the axis of rotation. So something is rotating. Let's use this chair, for example. So I spin this chair around, and very roughly, I mean, we probably want to break it down into smaller pieces than this, but let's just focus on like the two arms and the back of the chair. Those are our mass elements. So first I need an axis of rotation, right, because r is the distance from it. So let's just pick, the center axis of this chair that it's rotating on. And so this mass element, this arm, has some mass m and some distance r away. So one term of I is like this mass times r squared. This arm here has the same distance r away and the same mass. So we have mr squared of this arm plus mr squared of this arm. And then finally we'll add on this mass element too, the back of this chair, which has its own mass and distance r away. We just add all those together. And so we can see that the mass of an object is important, but also the arrangement of it is important. Yeah. It's from the axis of rotation. So the center of gravity and the axis of rotation are two different things because we can rotate something about anywhere. So like this chair, I chose to rotate it about this center point here, but I could also choose to rotate it like this, or any way I want to. And so they could be the same, but they're not always. The center of gravity is also a point. So there's like one point that's like the average of all the mass in the object. However, the axis of rotation is like as its name suggests, an axis. So the distance of this back to the axis of rotation would just be this distance, not this distance, if that helps. We're going to do some examples with this. But what this gives us is that it depends, like I said, on the object's mass, but also the geometry. So how we distribute mass affects it. If we increase the distance away that mass elements are from the axis of rotation, we'll increase the rotational inertia. We'll see what that means soon. And then also it depends on what the axis of rotation is. Like I just demonstrated trying to like awkwardly rotate this chair about the middle. You can choose different axes of rotation that are easier and harder to rotate an object. And so those will have different moment of inertias or rotational inertias. So an individual object can have an infinite amount of rotational inertias because you can rotate it around any point at any angle, any axis. So let's do practice. So first off, let's start with as simple as we can get, just a single object, this mass m, rotating around this point here, a distance r away, just circling around, rotating there. And so there's only a single mass element to add up, this one, and it has a mass m and a distance r. So here the moment of inertia, rotational inertia, is just mr squared. What if I double the mass, keep everything else the same, but make it 2m? Well, now if we plug it in here, the mass element is 2m, and it's r squared away, so we get 2mr squared. So we find double the mass, double the rotational inertia. What if instead of doubling the mass, I double the distance? So it's a mass m, 2r away. Well, now the 2r gets squared. So I get 4mr squared. So we see that both mass and arrangement, or like position of the mass, matter, but the geometry or the arrangement is actually more important, or it factors in heavier because it's squared. So rearranging an object and pushing the mass further away has a really big impact and increases the rotational inertia. All right, let's make it a little more complicated. Now let's say we have two masses, each a distance r over 2 away, and so it's like a dumbbell rotating about the center. So now we have two elements to add up, and so there's two terms here. Each of them has a mass m and a distance r over 2. So the r over 2 gets squared. We get two terms that are mr squared over 4. And so the total moment of inertia here, or rotational inertia, is mr squared over 2. So even though this object, this dumbbell, has twice the mass of the system we saw before, which is one mass m, a distance r away, even though this is heavier, with this configuration and this axis of rotation, it has a smaller rotational inertia. So it's easier to rotate this than it is to rotate that other system with one mass, a distance r away. What if we keep this same object? So now instead of changing the object, let's just change the point that we're rotating it from. So let's rotate it about one end point instead of the center. Now we still have two mass elements, but one of them has a distance from that axis of rotation of 0. Right? That mass is exactly at that point, and so it doesn't have any contribution to the rotational inertia. The other one is now a distance r over 2 plus r over 2, so a distance r away, and we get that this has the same rotational inertia as that original system, or as if that mass at the center of rotation wasn't even there at all. So you'll play around with these like wands in DL that should connect the physical intuition to these equations. But as you can see, the mass and arrangement are both important, and as is the axis of rotation. Yeah.
So are we measuring from the axis of rotation r to the center of mass of an object? Because like some of the diagrams, it would be edge of an object.
Yeah. So it's not. The center of mass is, I don't want to say like not important, but it doesn't factor in here. You have an object, and what matters is the distance from whatever axis I choose to rotate it from. So in this case, like let's use this bike tire. Right now it's rotating about this center axle. And so the distances would all be like from the tire to the center, like the radius of the tire. I could also take this off here and choose to rotate it like about here, in which case like the piece near my hand would have a distance of 0. This piece would have a distance of the diameter of the tire. This piece would have like something in between, So it could be at the center of mass like it is here, but it doesn't have to be. Another important thing is that it's the distance, like I said, from the axis, and not just the point of rotation. So like I said before, on this chair, if I'm rotating it, all these different points on the back of the, if I'm rotating it about the center, all of these points on the back of the chair have the same distance from the axis of rotation. So if you just imagine this like invisible line extending through the axle of this chair up, all of this back has the same distance from it. It's not just from like the point at which it's like connected, it's from the whole axis. So the vertical distance doesn't matter here. And we'll see lots of examples of that. So let's do a simple practice with this one. What is the angular momentum of the Earth revolving around the sun? So I'll just let you, I'm kidding, you need a lot more information for that. We'll do this one together. But the math for it is pretty simple once we're given the setup. So we know the orbital period of the Earth, like how long it takes to do one complete revolution, is a year, right? 365 days. So I can convert that into seconds, and we get like, I think that's 30 million-ish seconds. And then I'm telling us also the distance of the Earth from the sun is 1 times 10 to the 11th meters, and the mass of the Earth is 6 times 10 to the 24 kilograms. So with these 3 pieces of information, I can calculate the angular momentum of the Earth. And how do we do that? Well, the angular momentum, we need 2 things, the rotational inertia and the angular velocity. So first, let's do rotational inertia, because we just talked about that. If we want the rotational inertia of the Earth around the sun, then there's just one piece of mass, only one mass element, and that's the Earth, right? We don't include the sun, well, for 2 reasons, I guess. One, because I asked about the angular momentum of the Earth, not of like the whole system. The other is the sun is the center point, right? The Earth is rotating around here, so the sun would have an R of 0 anyway. So the sun doesn't factor in here. We just have one mass element, the Earth with its mass, that's this distance away. And so our rotational inertia is just mr squared, mass of the Earth, times the distance away from the sun squared. And we get this massive number, something like times 10 to the 47th. The units of rotational inertia are kilogram meters squared. I mean, you could see that from mr squared. They're not there's no like shorthand for that unit or other name for it. It's just what they are. Okay, so now we have the rotational inertia. It's huge. Now let's figure out what the angular velocity is. We know the angular velocity is delta theta over delta t. So first, let's just get the direction out of the way. This is kind of arbitrary based on the way that I drew it, but here the Earth is moving upwards. So from our perspective, it's counterclockwise, but if we take our right hand, wrap it in the direction that the Earth is moving around the center of the sun, we should get out of the page. So that's why I have this little circle with a dot in it. So there's our direction. And now we just need our delta theta over delta t. So for one complete rotation, 2 pi, it takes 1 year or 30 million seconds. And so I just evaluate that, and I get 2 times 10 to the negative 7 inverse seconds, or radians per second. So my angular velocity is actually tiny, which is kind of weird, right? The Earth we know it's moving very fast through space. It's this big object hurling through space, but the angular velocity is tiny. So the angular velocity is just saying how long does it take to complete a rotation, or like how many rotations per second, or however you want to phrase it. And the Earth does that pretty rarely. It makes it completely around the sun pretty rarely. So now to find the angular momentum, I just multiply these 2 things together, I times omega, and I get some huge number, 2 times 10 to the 40th, or 2.8 times 10 to the 40th kilogram meters squared per second out of the page. So yeah, the number here isn't particularly illuminating, but we see that maybe as we expect, the angular momentum of the Earth around the sun is pretty huge. Yeah. Yeah. So it actually, I don't think it would. So maybe this will become, like the concepts that I'm going to bring up are things that you will learn, and you might already, but I don't know. So what I'm trying to say is the explanation that I'm about to give, don't worry if it's a little hard. But because it goes in an ellipse, what actually happens is it speeds up when it's closer to the sun and slows down when it's far away. So it's actually like moving much faster at some points and slower at others. And that it works out such that the angular momentum is actually constant. Because when it's closer, I is smaller because that r is smaller, but omega is bigger. And so they actually, it works out so that it stays constant. But good question. We'll be dealing pretty much only with motion in a circle, so we don't have to worry about like those intricacies, but it is cool to think about. Okay, so we calculated angular momentum. One other thing I wanted to mention. So let's reconcile what I said before, which is like we know the Earth, like its tangential velocity, or its like linear velocity is pretty high. Or if you didn't know that, I'm telling you it is. Earth hurls through space at, I don't know, but it's measured in like kilometers per second, very, very fast. But we said we have this tiny angular velocity. Our angular velocity was like 10 to the negative 7 radians per second. And so to reconcile that, let's take a look at this demo right here. So we just have a plate. One mass is all the way on the edge. One mass is closer in. I'm going to spin it. And I want you to pay attention to how fast these are moving linearly. And so the best way to do that is just like focus your eyes on one. See how just fast it's moving. And then switch to the other. Switch back, switch to the other. Which of these is linear, like which one of these has a higher linear velocity? Like which one is just like moving faster through space? It's the one on the outside, right? The one at the very edge. This one is moving pretty slow compared to this one. You have to move your eyes a lot more to track it. What's the reason for that? Why is this one moving a lot faster? Well, if we think about the path that each one of these has to take to complete one rotation. So I guess first of all, let's note that they take the same amount of time to complete one full rotation, right? They're attached to this board, and so the amount of time it takes for this mass to leave and come back to its starting point is the same amount of time it takes this mass to leave and come back to its starting point, right? So they do have the same angular velocity because they complete 2 pi in the same amount of time. However, in doing that, in going around the center once, the mass on the outside has to trace out this big circle. So if I were to just like unravel that and hold it end to end, measure that distance, it's much larger than if I did the same thing for this inner mass, which traces out a much smaller circle. So if I were to unravel that, I'd get a much shorter line. And so if they do that in the same amount of time, the one that travels a lot further is going to have a much higher linear velocity, right? So so the Earth is super far away from the sun, and so even though it's rotating relatively slowly, like the angular velocity is very small, it's so far away that the circle that it has to trace out, or ellipse really, the path that it has to trace out around the sun is so long. It's so, I think millions of kilometers probably, I don't know if that's right, but it's really, really, really long, the Earth, how far the Earth has to travel. So even though it takes a year, that distance is big enough that the linear velocity, its tangential velocity, or how fast it's moving along that path, is really high, even though in order for it to get all the way around and back to where it started, in angular velocity-wise, is relatively small. Okay, so that's something you'll, again, see a bunch of examples and see how those things interact with each other. Let's talk about changes in angular momentum. So now we've talked about angular momentum, evaluated it for one system, and we know that we can change it by applying something like a rotational force, which is called a torque. So this, again, this like tau, this like curly T thing, tau net, for now we just understand it as the rotational equivalent of a force, but if you apply a torque to something, over time you get a change in angular momentum. So now we need to figure out what tau is, or like how we calculate it. How do we produce torques? How do we change the angular velocity of things? So to do that, let's, again, just look at this wheel and decide how I would change its angular velocity. So it's sitting at rest now, or relatively at rest. And so if I rotate it, I know that I will have acted on it with a torque, right? Because angular velocity now is 0. I rotate it. Now it's moving. It has some non-zero angular velocity. There was a delta L, and so that tells me I did create a torque. So what can I do to this wheel to make it spin? Well, I can apply forces to it, right? If I want to make this wheel spin, I just push it or pull it or something like that. But the things I'm doing to it look and are just the forces that we've been talking about this whole time, just applied in a specific spot and in a specific direction, right? Like this, I'm touching the top of the wheel here and then pushing this way. So that's a force in the positive x direction, whatever. But that force created a torque. Like there's some link here that also created a torque that was into the page. We can say into the page because, well, this wheel is rotating into the page. And so I gave the wheel momentum into the page. So there's some relationship between forces and torques. Let's just try a couple examples to see what types of forces do create torques and which don't. So like I just said, if I do this first scenario, or let's try the first scenario, hand on the right side of the wheel and apply a force up, that rotates it, so that did cause a torque. Put my hand on the top of the wheel and push to the left, that does rotate it. What if I grab the middle of the wheel, like this third example, and pull up? Nothing happens. That does not rotate it. So that does not cause a torque. What if I grab the top of the wheel, like in this fourth case, and pull up? That also does not rotate it. So we find that the location and the direction of the force are important and related to how much torque is created. And it turns out that, does anyone want to take a guess? What is a key difference between the forces here that do apply a torque and the ones that don't? Sure.
So if it rotates, then that means there's a torque present?
Say that again?
So if the object rotates, does it mean there's a torque present?
Just like with forces and momentum, just because something has momentum doesn't mean there's a force. You need a force to change it. So something can be rotating, but if it's rotating at a constant angular velocity or constant angular momentum, then there's no torque. If it's changing, so if like going from rest to rotating or rotating to stopped or speeding up or changing the direction of rotation, any change in L, the angular momentum, then there was a torque. Okay, so any key distinctions here? What differences are there between the forces that do create a torque and the forces that don't create a torque? Yeah. Very close. Not quite not to the axis of rotation, but to some vector related to the axis of rotation.
They're perpendicular to r.
Yeah, exactly. So I've drawn them all on here, and they're just like radii here. But what r is the vector that connects the axis of rotation to the point where the force is applied. So the axis of rotation for all of these is this center pivot point, and r is the vector that connects that point to where the force is. So like in this third example, the force is at the pivot point. So that's why r is 0. We can't even see it. But in order to produce a torque, we need force to be perpendicular to that r vector that we draw. Yeah. So yeah, that's a good point. That's kind of a new important thing now. Before, in our force diagrams, we would just kind of collapse everything to a point, right? Because it's easier. Like this object is a point, here are all the forces coming from it. Now, it turns out to matter where we apply the force. This r vector and its direction matters. And so yes, these are called extended force diagrams. We'll do a lot more with these and see them explicitly. But yeah, in this case it matters. So now we have kind of two versions of force diagrams. If you just care about the force and linear stuff, not angular momentum or rotations, you can collapse them all down to a point. But if you want to describe rotations and use diagrams to talk about them, then yeah, it is important. And where you draw the force is like, this is where the force is acting. Because this same force translated to a different point, like the center, will have a big impact on whether or not it creates a torque. Okay, so we need a perpendicular amount of the force. Like we need the force to be perpendicular to its position vector from the axis of rotation. And then the other thing we need, I guess we haven't proved it on this slide, but kind of hinted toward it, is we need to have some distance period from the axis of rotation. So any force that I apply that is exactly at the axis of rotation also can't apply a torque, right? So like, here's my wheel with an axle going through the center. There's no, well, I'm not exactly at the center, but there's no force that I can apply in any direction with no r vector away, like with zero distance from the axis of rotation that can cause it to rotate. I always need some distance away. So again, the location matters. It needs to be separated from the axis of rotation, and the direction matters. It needs to be perpendicular to the vector that connects the axis of rotation to where that force is. And so the expression we have for torque, it's exactly that. It's the perpendicular piece of the force times the vector r, or times the magnitude of the vector r, so times the distance away from the center of rotation. So we could see here that, maybe obviously, increasing the force increases the torque. So here's a force that applies a torque. If I apply a larger force, I get a larger torque, a larger change in angular momentum. That's kind of straightforward. But r, also, if I increase r, I increase the torque. And we can see that if I push on the wheel very close to the center, so with a small r, with some force, it causes some torque, right, and some change in angular momentum. But if I apply that same force, so roughly, you just have to trust me that I'm applying the same force, but if I apply that same force with a larger r, now closer to the rim, further from the axis of rotation, I get a much larger change in angular momentum, or a much larger torque. So same force with a smaller r gives me a smaller torque. Same force with a smaller r gives me a smaller torque. So increase force, you increase the torque. Increase r, you also increase the torque. And that kind of builds in here. If r is 0, in other words, if the force is right at the pivot point, you're not going to get any torque. So then the last important thing here is this F perpendicular. Not all forces are perfectly perpendicular to r, or like perfectly parallel, in which case we know that they cause no torque, right? A lot of them are going to be in between. Like I could apply a force to this wheel that is like diagonal, in which case, it does rotate a bit. And so we have trig for that, right? So when we have, well, I guess this is what I should have just pulled this up before, but here are the two extremes, right? A force that's perfectly perpendicular and a force that's perfectly parallel, in which case the perpendicular component of the force is 0, but the force is not 0 itself, but this would produce no torque. So what if we have like an in-between like this? So now we have a force that's applied to the edge of this wheel, and it's not perfectly perpendicular or parallel to r. But what we can do is find components of it, right? Now, except instead of caring that, oh, this is x and this is y, what I really care about is that one component is parallel to r, and that component does not contribute to the torque, right? That would just be like pulling on the edge of this wheel away from the center, so it doesn't create a torque. But then there is a component of F. In this case, it happens to be the vertical component that's perpendicular to r. That's the piece that contributes to the torque. So when I'm calculating the torque from this F vector, it's not just F times r. It's the perpendicular component of F times r, which in this case we happen to get from sine. So based on this triangle here, F perpendicular is opposite the angle we're given. And so F perpendicular is the magnitude of F times sine theta. And so the torque we get here is Fr sine theta. Yeah.
You also use F parallel with the cosine theta?
That is how you would find F parallel, but F parallel does not contribute to the torque. So we wouldn't want it in this case. In some problem, there might be something like aside from the torque that we might need it for. Like it does exist, but if we're just calculating torque, you never want F parallel. Yeah, so that's R. So R is often called the moment arm, and hold on that for a sec, because the definition for moment arm can be a little bit different, and this next example illustrates that. So here, what we found is we found the piece of F that's perpendicular to R. However, we can also do the opposite. We can find the piece of R that's perpendicular to F. And it turns out those are mathematically the same, and one will sometimes be more convenient than the other. So let's take this case. Now we just have like some plank rotating about its end by us applying a force to the other end. So we can see here that the plank acts as like its own position vector here. R is the vector that extends from the center of the rotation, the axis of rotation, to where the force is applied, and the force is applied straight down. So R and F are not perpendicular, and so we need to break them down into components that are. However, in this case, F is already vertical, right? F is already in the negative y direction. It's pretty to look at. R is the one that's diagonal. And so it doesn't really matter, but I think here it's easier to think about breaking R into vertical and horizontal components. So this way we never have to deal with any axes that are anything but like x and y. And so we can find the x and y components of R. Here the y component, the vertical piece, is parallel to F, so that's the piece we can ignore. And the horizontal piece, R perpendicular, is the piece that's perpendicular to F. So in this case, we find that R perpendicular is R cos theta. It's the angle that's adjacent to theta. So here we do sometimes use cos, but it's still to find R perpendicular, never the parallel component. And so now we plug in for the torque, and now it's F times R perpendicular, but we still get magnitude of F times magnitude of R times some trig function, which is less than or equal to 1. So cosine theta, sine theta, whatever it ends up being, is always going to shrink or keep the same, whatever this quantity is. Meaning that if they're perpendicular, if theta is 90, it's just magnitude of this times magnitude of that. And if theta is smaller than 90, or like anything but perpendicular, then we'll get some value less than them, because some of the force is like wasted, not producing a torque. It's just like pulling on the rim or something like that. So either way you do it, F perpendicular times R or F times R perpendicular, you get the same thing. And so with the moment arm, some people call, or maybe even the technical definition of moment arm is that it's R perpendicular. So it's like just the piece of R that is perpendicular to F. Other places you might see people call the moment arm whatever this R is, and then you just find like the F perpendicular, but that's why, I don't know, I don't love that language. At the end of the day, like the two important vectors are what the force is and what the force's position vector is, and then we need to find the amount of those two that's perpendicular. So we could still find F perpendicular here, right? And I can do that on the board real quick. Sorry if you're watching this online, but I'm just going to draw the same. Do this many times in DL and stuff. Instead of breaking R into components, I see it's easy here, but I want to find F perpendicular. The general way to do this is, since R is my like reference, right? I want to know how much of F is parallel and how much is perpendicular. I'm going to just draw axes that are parallel and perpendicular to R. So the parallel one's easy. It's just the axis that is along R, and then the one perpendicular is just the axis that is perpendicular to that. And so now I have another set of diagonal axes. Here's my perpendicular one, and here's my parallel one. They're not our normal like x and y, vertical and horizontal, but that doesn't matter. They're just two perpendicular axes that we can find components for vectors. And now F has a component that's perpendicular. Here's my F perpendicular, and F has a parallel here that we don't care about. But this parallel piece is parallel to R, and we would actually find, if we're given this same angle theta here, if this angle is theta, you can do some geometry and find that this angle is also theta here, and you find that F perpendicular is just magnitude of F times cos theta. And again, this way now, we find that F perpendicular times R is equal to F R cos theta, which is exactly the same as if we had found F times R perpendicular, like I did on the board. So either way is correct. Again, this is just another one of those cases where one way is more convenient than the other, and I think that way is pick whichever one, F or R, is already vertical or horizontal, and use that as your reference. That way you can stick in your normal thinking about like X and Y. But if neither of them was perfectly vertical or horizontal, that's fine too. Again, you just need to pick one as your reference, make axes, and break the other vector down into components along those axes. I know that's a lot to like take in here, but this is something that, again, just you need to practice a bit. You know all how to work with vectors at this point, how to break them into components, and so this is just generalizing that a little bit. And of course, there will be kind of like some funky situations where you need to, where it might just be hard to see how to break it down. Yeah. Oh, okay. This one probably not, but that's in DL, and I'll put it on like practice quizzes and stuff like that. So, but this chalk drawing won't be up there. You'll get plenty of opportunities to see that. And it's good practice whenever, like if you're in DL and you finish early, or you're doing an FNT and like you're getting sad that it's ending soon and you want to keep it going, then a good thing to do is just, you did a problem doing, like let's say you use the FR perpendicular method, try it again. I guess you don't have to repeat the whole thing, but just do the steps again where you would do it the opposite way. So instead try finding F perpendicular R. Doing each problem both ways just takes an extra minute or two, and it really solidifies your ability to see both and recognize that there's not like some special FR sine theta or FR cos theta or whatever formula. At the end of the day, we have these two vectors, and we just want to find the perpendicular amount of each of them. Okay, so now connecting this all back to angular momentum. So this is just our like how we define torques. We have our angular velocity, which is our change in angle over time. And that's just, describes how fast something is rotating. But then not all things that rotate with the same speed have the same like angular motion, right? There's some concept of angular mass, which is our rotational inertia. It's very important. And so we learned how to calculate rotational inertia, I, and we can multiply that by our angular velocity to get angular momentum. And then finally, angular momentum, that just describes the instantaneous angular momentum of something, like how much rotational inertia means I, but like how much motion it carries rotationally. And we can change that by applying torques over time. And we found that torques are produced by forces, but particularly what's important is not just the force itself, but the angle with respect to its position vector and what that position vector is. So the further away a force is from the axis of rotation, and the more perpendicular it is to its position vector from that axis of rotation, the larger the torque produced. So torques cause a change in angular momentum, and that can be just like with momenta, right? You can apply a force that speeds something up or slows it down, but you can also turn it, right? You can change the velocity of something without changing the speed by just changing the direction. We don't see that as much in this because it just gets really difficult to think about spatially, but you still can change the direction of angular velocity without changing its angular speed. And one way to see that maybe would be with this like bike tire. So this is something we'll get into more next time, and also I think you see this in DL. But if I just hold it like this and spin it, now it has some angular speed, right, and angular velocity, and I can turn it and change its angular velocity, change the angle, like change the direction of that vector, but without changing the speed, right? So it's still rotating at the same speed, but as I turn it like this, I'm changing the direction of the angular velocity, which does take a torque. So that gets a little bit, interesting but tricky. And again, we'll leave that for DL and next time. But basically any rule or pattern that you see in linear momentum problems has an analog here. It's just maybe one extra level of work from your spatial reasoning skills. Okay, so that's all I have today. One more comment I wanted to make. Today I just gave you like a in some places rough overview of angular momentum and torque and stuff like that. What you're going to be doing next in DL, or at least like to open up, is mostly problems where delta L equals 0. And usually just L equals 0, so balanced torques. Meaning that if you have angular momentum, it's constant or just 0, and you're just going to practice evaluating, I have a bunch of forces at a bunch of different points. How can I make those torques balance? Or like checking whether they balance and stuff like that. And then once you get comfortable with that, then we'll move on to actual changing angular momenta and things exchanging angular momentum. We'll save that for next time, but it's the same arc that we did with linear, where we started with just like net force equals 0, balancing them all out, and then we moved progressively until we reached like multiple objects exchanging momenta. So we'll do the same thing here. Okay, thanks.